Alright, in this video we're going to talk about some pretty advanced examples of using max flows. So in the first example, we are in the situation where we're playing an online mini golf game. Looks something like this. But something went wrong in the programming department, and so they lost which holes go to which starting points. And so we need to reconstruct that to figure out how to solve the game. So in particular, we know the locations of the starting points in the holes, but which starting points go to which holes was lost. So we're in this situation here where we don't know which ones go to which, but we want to figure out and pick a correspondence between starting points and the holes. So the input consists of the XY coordinates of the M corners of the playing field. So we know, say, these corners, but we don't know the exact line segments making the border. But we do know that the borders are always meeting at right angles. And so we can always reconstruct the line segments from just the points. We're also given the n starting points and the n holes. And we can assume in constant time, we can determine whether two line segments intersect, given their x and y coordinates. So, like I just said, given xy coordinates, there exists a formula that lets you quickly check whether the two segments intersect. And we want to figure out which holes go with which starting points. So naturally you might be thinking, okay, we're literally matching holes to starting points, so must be some kind of bipartite matching problem. And you would be right. So the bipartite graph is going to have the starting points in L, the left side, and the holes in R, the right side. So we just take our input points and just slap them right into L and R. Now the edges are a little more complicated because for a specific starting point S and a hole H, we'll have an edge between S and H in our graph only if the line segment from S to H would not intersect any of the border line segments. So how do we check that? Well, we can check it in O of M time by literally computing every single, by looking at two pairs of points on the border, we can compute the line segment, and then we just use the constant time algorithm we're assuming we're given, this one right here, and just check would this line segment intersect the line segment between that hole and that start point. So we can just brute force one by one check, one by one check, one by one check, and if after checking all of them, of which there are roughly M, there's slightly more than M of these line segments, then we can verify that's an edge. So in O of M time, we just brute force check each of the line segments on the border, don't intersect this line, and if so, it becomes an edge. So then the idea is just we can reconstruct the paths, or we can find the goal line segments, the line segments that's supposed to match a starting point to a hole. We can reconstruct those if and only if there's a perfect matching in this graph G we are constructing. So visually, you can think of this as L would be the stars in that picture, or sorry, those are the open, oh yeah, the stars at the starting points. So we have the stars become our L, we have each of the holes become a node in R, and then we have an edge between them if it's possible for that hole to be matched with that star without it hitting a border. So for example, if we had maybe this is the first star and maybe this is the first hole, then we actually don't have an edge there because connecting them would cause you to go over the border. However, hole 2, there is an edge there because it is possible to connect them. So that's what our graph would look like. So we create the graph, and then the key theorem here is we can reconstruct the paths exactly when there exists a perfect matching. So what are we going to actually do? Well, we'll run the bipartite matching algorithm on G. We know how to do that from a reduction to max flow. And then we just check if the resulting matching, the maximum one, has size n. If it has size n, that means every single hole has been matched to some starting point. And so we've done it successfully. Now, what's the running time of this algorithm? Well, the vertices are 2n, one starting point, one hole, and then there's at most n squared possible edges because each pair of start to hole could have an edge between them. And it also takes O of n times m to build the graph G. So typically building the graph G is pretty straightforward. It's a low time. But in this problem, if m is really big, this could be the dominant running time. So we have to be careful of how long it takes to build G here. So the matching algorithm is going to take O of n cubed time because if we use, say, well, we just know the matching problem takes O of e times e, and so because these are both n and n squared, we get n cubed. So the total will be O of n cubed for the matching part and O of nm for building G. And we can't remove either of them because m could be possibly huge. So maybe you have just one hole and one starting point, but a ton of borders, in which case this part will dominate. Otherwise, if m is pretty small, then this part will dominate. So that's how we do this. Now to prove the lemma formally, you can just, take any path, take any set of line segments and turn it into a perfect matching and vice versa. It's super straightforward to do, so I won't do it, but you can convince yourself that that's true. Okay, so now here's a little harder example, and I guess by little harder, I mean it's way harder. So this is the domino tiling problem. So in this problem, you're given some checkerboard, but certain spaces are removed. And the question is, if you place dominoes, can you place dominoes on the board so that every single square is covered? And you can't overlap the dominoes. So each domino has to be disjoint from the others. We can't ever have a situation like this where dominoes are shared, or some square is covered by multiple dominoes. So how do we solve this one? Well, intuitively, it's going to be similar. For each domino, we want to match it to two squares. In particular, these have to be adjacent squares. So we want to somehow construct a graph and compute a matching that will assign each domino to two squares. And in particular, we want a perfect matching so that every single domino covers two squares and every single square is covered by some domino. But it's a matching because we can't have any domino. Two dominoes should not share a square. They need to be separate. And then we can also take into account which squares aren't existing in the graph. So this is the idea. Now we can't literally do that because you cannot match one thing to two things. The whole point of the matching problem is it has to be a one-to-one thing. So you can match a single domino to a single square, but you can't do it to two. So we need to use the general assignment problem framework. Or tuple selection, if you prefer. And we can do something like assign a domino to an initial square. And then once we decide the initial square, we can then decide the next square. So overall, we are placing a domino on two squares. So that's going to be the idea. Now the tricky part is which squares go in this set and which squares go in this set. We could have the same, we could have every possible square in both, but then there's the danger of one domino covering multiple of the same square, or some square or some domino is on top of two squares that aren't even close to each other at the same time. So we have to be really careful with how we're constructing these sets. So one useful thing to do will be to partition the board into two parts, indicated in the picture. So we have the white squares, which we will call O for the odd set. So basically, these are all in the first row, these are the odd squares, and then each odd square is touching even squares. So then we have the even set, which end up being the gray squares. So that's the idea. And then we can mathematically define these sets by the even set is the set of ij, where I is even, so we pick an even row, and j is odd, so it's the gray squares, and we need that it's not deleted. So this is where the deleted array is coming into play. Or if we look at the odd rows, so if I is odd, then it's going to be the even squares. So here we have this square and this square are the gray squares, and these are in even positions on an odd row. And similarly, we can define O to be the white squares so that I is odd and j is odd. So here are the white ones, or I is even and j is even. So those. So we can create these mathematical definitions of these sets E and O, and we can construct these efficiently because we can just loop through each possible square in n squared time and just check, is my current I even, my current j odd, and is this array entry true or false? So we can construct both of these sets in O of n squared time. So we'll use these sets to help us build our graph. So we're going to make this an assignment problem. And the idea is first we need to define this number m. So m is going to be the total number of squares to cover. So these are just all the not deleted squares. Now if m is not even, so if m is odd, we return false immediately because we're using a single domino to cover two squares, right? So in total, we need m over two dominoes, two squares per domino. So obviously, if this isn't even it isn't even an integer if m is odd. And so obviously we can't cover the whole board. Similarly, if there's more odd squares than even squares, then it'll also be impossible. And this is because each domino will cover one even and one odd, because that's just how adjacent squares work. Every adjacent square, which means up, to the right, to the left, or down, each adjacent one has to be a different color. So let me just say that. Each adjacent square is a different color than current square. So every time we place a domino on two squares, we're placing it with one gray and one white. So now we can kind of see how it's a matching problem. We're going to match it to a single gray and a single white. So these sets will become gray and white respectively. Okay. So we're matching dominoes to even and odd squares in order to cover it. So what's this graph going to look like? Well, we have, just like in normal tuple selection problems, we'll have some S and T. We'll also have our even and odd squares, or you could call them the gray and white. So this one's gray, this one's white. And then we have a set of numbers from 1 to m over 2, which corresponds to each domino. And then this is what the graph looks like. So because it's tuple selection, we'll have a single source S connected to each domino, each with capacity 1. Then we'll have a single sink T that touches all the odd squares, and i.e. the white squares, and this will also have capacity 1. Then we have a fully connected subgraph here, so for every pair of domino to even square, we allow the possibility that that domino is matched to that square. There's no bias between which of these squares is better for domino 1 or domino 2. On the other hand, there are differences between E and O. So we only have an edge from some square ij to possibly 4 other squares, the adjacent squares. So we only have an edge from a square in E to a square in O if they were adjacent on the board. So for example, this would be the square to the right, this is the square to the left of ij. So this is what our flow network will look like. And formally, we have edges for any ij in the even set. If ij is an even, so it's in this category, and if we know ij plus 1, the adjacent to the right, is an O, then we'll have an edge. If it's not an O, that means that it was deleted. And we don't want to consider deleted squares here. So NO is just a shorthand way of saying and was not deleted. So these are all the edges that correspond to an even to an odd. It's any possible adjacent square that wasn't deleted. So that's our full graph. And again, the idea is for each domino, we assign a domino to an even square and an odd square to cover, specifically an odd adjacent square. So we always imagine we start with even squares, and then we move to the odd ones. But this still covers all cases because, let's say for example, here we started with an odd square, or we always start with we start with an odd square. So how do we cover this one? Well, remember, this will be adjacent to the gray one. So instead of thinking of putting the domino, laying it down first here and then laying down the rest there, we think about placing the domino first here and then lay it down on that one. So we're still getting all possible squares, even though we're thinking of it as putting it down on E first. But this won't cause any issues with the covering. So what's the problem? Well, we want to find a perfect matching. It's not actually a matching because there's 3 things, but it's basically a matching in G. So to do that, we're going to compute the max flow in that graph G prime, basically solving the tuple selection problem, and then we just check if the max flow value is m over 2. If it is, that means every single domino was matched to something, and so every single square is covered. The algorithm we'll use is Ford-Fulkerson to compute the max flow, and then we compute G and the final check, this final check, by brute force. So overall, our running time is going to be dominated by Ford-Fulkerson because constructing the graph G is pretty fast. Specifically, just by brute force, there are n squared possible nodes for each cell, and then there's possibly n cubed edges, just because right here this is fully connected. So if you have roughly n squared stuff and roughly n squared stuff, then the total number of edges between them is going to be, actually that's n to the 4th. Right. Because you have roughly n squared things here and roughly n squared here. To be more precise, we could actually do the running time in terms of capital M, but in the worst case, capital M will basically be n squared anyway. So also notice that Ford-Fulkerson, the value of the flow will always be at most m over 2, and so that's n squared value for the flow. And so Ford-Fulkerson is going to run in time O of n squared for the value times the number of edges. So now that's a 6. So this is a 6. Sorry, this is a 4, and so this is a 6. But in terms of the original input size, so the full input size m, which is basically the whole board, is size n squared, which is just the size of a side. And so if we're bounding the running time in terms of the original input, it's actually O of m cubed. So it's not actually as bad as this might make it seem. It is a really complicated problem, so it makes sense that it'd take a while. So now we have to prove it's correct. Again, it's pretty straightforward. There is a valid placement of dominoes if and only if the max flow in G is m over 2. So what's the idea here? Well, if there is a valid placement, and say domino K is placed on cell ij, which is even, and cell I prime j prime, which is odd, then what we can do is send one unit of flow down the path S to K to ij to I prime j prime to T, and we know this is a valid path. This path is in G by construction, because if it's a valid placement, this I prime j prime has to be adjacent to ij. And if it's a valid placement, it has to be odd. So by construction of the graph, that path will exist. And because it's a valid placement, no dominoes are stacked on each other, and so the capacity constraints will never be too high. We'll never put multiple dominoes on the same cell, and so the flow going through ij will never be more than 1. And then obviously, the value of this flow is going to be exactly m over 2, because that's the number of paths / number of dominoes used. Okay? Now for the other case, let's say f star has a flow of size m over 2. Well, then we can do the following. We place domino K on cell ij and I prime j prime if this was the path. Specifically, we find the path in the flow decomposition of f star. Or because this is a simpler graph, we just have to find a path of unit flow by doing a whatever for search. And we know it's all unit flow by the integrality theorem because our capacities were all integer. Specifically, they're all capacity 1. But we're not actually computing the flow decomposition in this problem. We just need the final answer, so we're just doing this in the proof. We're just using the fact that a flow decomposition theorem implies that we can break up the flow into a bunch of paths. All right, so is this a valid placement? Well, we know each domino is placed, and we can check for overlaps. So remember that m over 2 is like the minimal number of dominoes we need to pull this off. So overlaps isn't an issue. So there's no overlaps. No overlaps. So long as every cell is covered. So we really just need to check every cell is covered. Well, suppose some cell ij is not covered. If it's not, that means no domino, and let's just say for simplicity it's an even one, that means no domino was assigned to it, But because there are exactly m over 2 dominoes, that implies two dominoes must have been assigned to the same E. So 2 dominoes were both assigned to the same cell, a different cell than ij, but that would invalidate the capacity constraints. So that's not possible. So this would contradict the capacity constraints. And integrality. So integrality is really important here. So you could do something like send some unit of like 1/2 down here and 1/2 down here, but because it's an integral flow, that is impossible. So we know all ij from the even are covered, and then you can also argue all the odd ones are covered. But that's the main idea. And so that's the algorithm.